Okay, so let's look at a different combustion analysis problem. And so before you begin, two things. I would write down the information, pause the video, write down the information in this problem. Since this is such a long problem, I'm going to shrink this text really small so you might not be able to read it anymore. And then I would also look at the steps that we outlined in class for this problem. And those steps are: find the moles of carbon dioxide in water. Once you have the moles of those, then you want to find the moles of carbon and hydrogen alone. Once you do that, then you want to find the moles of oxygen. To find the moles of oxygen, you'll have to find the mass of carbon and hydrogen and subtract that mass from the mass of the original sample. And then you can find the mass of oxygen. Once you find the mass of oxygen, you can find the moles. If you have the moles of each element, then you can write your empirical formula. And then if you take the molar mass of your empirical formula and the molar mass of the molecular formula and divide those two numbers, then you can find out the whole number multiple that you'll need to multiply each thing by in your empirical formula in order to calculate or figure out the molecular formula. And we'll go through each step, but that's just an overview of the steps. You should write out those steps in words and follow them as we're solving this. Okay, so you have vitamin C. It has carbon, hydrogen, and oxygen in it. You have a 1 gram sample, and then you combust it. You have a mass of carbon dioxide and a mass of water, and so you want to find the molecular formula. So the first step is using the mass of carbon dioxide and the mass of water in order to find the moles of carbon dioxide and the moles of water. So let's do that. You have 1.50 grams of CO2, and then you have 44.01 grams of CO2 for every 1 mole of CO2. Alright, so that gives you, right, your units cross out, that gives you 0.03408 moles of CO2. Since I know already we're going to have to find the moles of carbon, I'm just going to note, right, that we found this, but continue this calculation. For every 1 mole of CO2, there's 1 mole of carbon. So we have 0.03408 moles of carbon. Okay, so let's find the moles of water and then the moles of hydrogen. So if we have 0.1 grams of water, the molar mass of water is 18.02 grams for every 1 mole of water. And this equals 0.02275 moles of water. So let's find the moles of hydrogen. Let's just keep on going with this calculation. For every 1 mole of water, we have 2 moles of hydrogen. So the moles of hydrogen are 0.0455. Alright, So we have two pieces of the empirical formula that we need to find the empirical formula. Now we need to deal with oxygen. So if we know the moles of carbon and of hydrogen, we can find the mass of each as well. So let's find the mass of carbon and the mass of hydrogen. So if we have 0.03408 moles of carbon, to find the mass we need the molar mass of carbon, which is, if you have 1 mole of carbon, you have 12.01 grams of carbon. So you have 0.4093 grams of carbon, and then for water, 0.0455, or I said of water, I meant of hydrogen, for every 1 mole of hydrogen. So let me just say, you might be tempted to not want to do this multiplication because the molecular mass of hydrogen is approximately 1, but you will get a different answer sometimes and it will mess you up. So do not take a shortcut. Do this multiplication. So you get 0.04586 grams of hydrogen. Okay, now that you have the grams of hydrogen and the grams of carbon, we need to subtract them from the original sample, the grams in the original samples. So since there's just 1 gram in the original sample, I'm just going to do this in my calculator. So I'm subtracting 0.4093 and 0.04586 from 1. The reason I'm choosing 1 is because that's how much original sample we had. Minus 0.4093. Okay, so the mass of oxygen I get is 0.5448 grams of oxygen. If I know the mass of oxygen, I can find the moles of oxygen, and then I'll have all of the information I need for my empirical formula. So to find moles of oxygen, I need the molar mass of oxygen. So oxygen is 16 grams for every 1 mole. So you get 0.03405 moles of oxygen. Okay, so now we have our moles of carbon, right? So we have our moles of carbon, our moles of hydrogen, and our moles of oxygen. So we can write our empirical formula. I'm going to make all of this pretty small. Okay, so we have carbon, hydrogen, and oxygen. So the amount of hydrogen or carbon that we have, is 0.0341. The amount of hydrogen in moles is 0.046. The amount of oxygen is 0.0341. We have the same moles of carbon and oxygen, so we could divide by either one. It doesn't matter, it will be the same. But it's the smallest number of moles. I forgot O there. So when we do this, we get carbon is 1, hydrogen is 1.3, and oxygen is 1. So here's something that is a little tricky that we didn't get to in class today. So hydrogen is not a whole number. We need for hydrogen to be a whole number. In order for hydrogen to be a whole number, we have to think about what we could multiply it by in order to get a whole number. So if you notice, this is 0.3 here, we have 0.3. If you have 33 and you multiply it by 3, then you'll get a whole number. So if we multiply 1.3 times 3, we'll get the number 4, and that's a whole number. So we know that we need to multiply each by 4. So this would be 1 times 4, 1.3. I'll write it more clearly. 1.3 times 4, and then 1 times 4. I just said 4. I'm sorry, I meant 3. Because 1.3 times 3 would be 4. It's a whole number. Okay. So 1 times 3, 1.3 times 3, and 1 times 3. So the empirical formula then that we have is C3H4O3. This is our empirical formula. But we're not done with this problem yet, because we have to find the molecular formula. So I'm going to make all of this small again. So in order to find the molecular formula, we have to find the whole number that we want to multiply each of these subscripts by, right? To get the right ratio of atoms or elements, right, in this compound. So we need to find N. So N is equal to the molar mass of vitamin C we're given that in the problem, divided by the molar mass of the empirical formula. So N is equal to 172.12 grams per mole divided by the molar mass of the empirical formula. So 3 times 12, so the molar mass of this would be the molar mass of the empirical formula. So we have 3 times 12.01 plus 4 times 1.008 plus 3 times 16.00. So this should give us 88.06 grams per mole. Once you divide these two numbers, you get 2. So to go from empirical formula to the molecular formula, you have 3 times 2, 4 times 2, and 3 times 2. So you should get C6H8O6. And that is the molecular formula for vitamin C. The really great thing about these problems is that you can check yourself. So you can check and make sure that the molecular weight of this molecular formula is equal to the molecular weight that was given in the problem. So if you did this, you would have, let's see, 6 times 12.01 plus 8 times 108 plus 6 times 16, and you get 176.12. So you know that you did it correctly.